Welcome to our cosmic crash course. Today we'll embark on a thrilling journey through the cosmos, exploring some of the most groundbreaking theories in physics. From the elegant laws that govern the motion of planets to the mind-bending world of quantum mechanics, we'll unravel the mysteries of the universe and meet the brilliant minds who dared to unlock its secrets. Get ready to understand the universe in a fun and easy way. Picture an apple falling from a tree. A simple act, yet it sparked a revolution in scientific thought. Sir Isaac Newton, a man of profound insight, saw beyond the mundane and unveiled a fundamental force that shapes our universe: gravity.
Newton's law of gravitation is like a cosmic glue that holds everything together, from the smallest apple to the largest galaxy. It's the reason why apples fall from trees, why the moon orbits the Earth, and why the planets dance around the sun in a celestial ballet.
This invisible force depends on two crucial factors: the mass of the objects and the distance between them. The more massive an object, the stronger its gravitational pull. Think of a bowling ball on a trampoline compared to a tiny marble. The bowling ball creates a much larger dip, representing its stronger gravitational field. Similarly, the closer two objects are, the stronger the force between them.
Gravity's influence is far-reaching. It keeps our feet firmly planted on the ground, prevents the Earth from spinning out of control, and binds our solar system together.
In the early 20th century, a young Albert Einstein dared to challenge the very fabric of our understanding of space and time. With his theory of relativity, he ushered in a new era of physics, forever changing our perception of the cosmos.
Einstein's special theory of relativity, a symphony of space and time, revealed a profound truth. Time and space are not absolute but are intertwined in a cosmic dance. Imagine a train speeding close to the speed of light. To an observer on the platform, time on the train would appear to slow down, a phenomenon known as time dilation.
And then there's the iconic equation E equals mc², a masterpiece of scientific brevity, revealing the profound connection between energy and mass. It tells us that mass can be converted into energy and vice versa, a concept that revolutionized our understanding of the universe and paved the way for technologies like nuclear power.
But Einstein wasn't finished. He delved deeper into the cosmos, expanding his theory to encompass the force of gravity. General relativity, his crowning achievement, paints gravity not as a force acting at a distance, but as the curvature of space-time itself. Imagine space-time as a vast, flexible fabric. Massive objects like stars and planets create depressions in this fabric, much like a bowling ball on a trampoline.
Objects like planets don't simply move in straight lines, they follow the curves created by these massive objects, explaining why planets orbit stars and why we remain grounded on Earth. Einstein's theory of relativity revolutionized our understanding of the universe, revealing the interconnectedness of space, time, gravity, and the very essence of existence.
Quantum mechanics, delving into the realm of the ultra-small. In the heart of the atom, where the laws of classical physics falter, lies a realm of bewildering wonders, the quantum world. Quantum mechanics, the physics of the ultra-small, challenges our intuition and reveals a universe stranger than we could have imagined. One of the most mind-boggling concepts in quantum mechanics is wave-particle duality. Imagine a beam of light passing through two slits. Instead of creating two distinct lines as you might expect, it forms an interference pattern, like ripples on a pond, suggesting that light, traditionally thought of as a wave, also behaves like a particle. This dual nature, both wave and particle, extends to all matter, blurring the lines between what we thought were distinct entities.
Another cornerstone of quantum mechanics is the uncertainty principle, a concept that shook the very foundations of determinism. Introduced by Werner Heisenberg, it states that we cannot simultaneously know both the exact position and momentum of a particle. The more precisely we measure one, the fuzzier the other becomes.
Quantum mechanics also introduces the perplexing concept of superposition, where particles can exist in multiple states at once until they are observed. Imagine a coin spinning in the air. It's neither heads nor tails until it lands. Similarly, in the quantum world, particles exist in a probabilistic haze, a superposition of states, until a measurement collapses this wave function into a definite outcome. quantum mechanics reveals a universe far stranger and more wondrous than we could have imagined, a realm where the very act of observation shapes reality.
The Big Bang. Echoes of a cosmic dawn. For centuries, humans have gazed at the night sky, pondering the vastness of the cosmos and the mysteries it holds. Where did it all begin? How did this grand cosmic tapestry come to be? The answer, as revealed by modern cosmology, is as awe-inspiring as it is profound: the Big Bang. In the 1920s, I made a groundbreaking discovery. By observing distant galaxies, I found that they were moving away from us, and the farther away they were, the faster they were receding. This observation, now known as Hubble's law, provided the first compelling evidence that the universe is expanding.
If the universe is expanding, then it stands to reason that it must have been smaller in the past. Extrapolating backward, we arrive at a point of unimaginable density and temperature, the singularity, where space and time as we know them cease to exist. This is the Big Bang. Around 13.8 billion years ago, this singularity exploded in a cataclysmic event, marking the birth of our universe. In the first fleeting moments after the Big Bang, the universe was a seething cauldron of energy. As it expanded and cooled, elementary particles began to condense from this primordial soup, forming the building blocks of matter.
Over eons, gravity drew these particles together, forming stars, galaxies, and the vast cosmic structures we observe today. The Big Bang wasn't just an explosion of matter and energy. It was the birth of space and time itself. As the universe expanded, space stretched, carrying galaxies along for the ride. The Big Bang theory has revolutionized our understanding of the universe, revealing its origins, its evolution, and our place within its grand cosmic narrative.
Heisenberg's uncertainty. Principle: embracing the fuzzy universe. Imagine trying to pinpoint the exact location of a tiny, fast-moving particle, like an electron. You shine a light on it, hoping to catch a glimpse of its position. But here's the catch. The act of observing the electron of bouncing light off it alters its momentum, its speed and direction. This inherent fuzziness, this fundamental limit to our knowledge, is at the heart of Heisenberg's uncertainty principle.
This principle, a cornerstone of quantum mechanics, tells us that we can never simultaneously know both the position and momentum of a particle with absolute certainty. The more precisely we try to determine one, the fuzzier the other becomes. It's as if nature imposes a fundamental trade-off between these two properties.
To understand this, imagine an electron as a wave packet, a blurry cloud of possibilities rather than a tiny, well-defined point. When we measure its position, we're essentially forcing this wave packet to collapse, to become more localized. But in doing so, we lose information about its momentum, which becomes more spread out. Conversely, if we try to pin down its momentum, its position becomes more uncertain. This inherent uncertainty isn't a sign of our ignorance, it's a fundamental aspect of nature.
The universe at its core is inherently probabilistic. We can only talk about the probabilities of finding a particle in a particular state, not its exact state with absolute certainty. This principle challenges our classical intuition, where we're used to thinking that objects have definite properties, that we can know both their position and speed with arbitrary precision. But in the quantum world, we have to embrace a new way of thinking, where uncertainty and probability reign supreme. So there you have it, our cosmic crash course. We've journeyed from the falling apple that inspired Newton to the mind-bending world of quantum mechanics. We've explored the vastness of the cosmos, from the birth of the universe in the Big Bang to the intricate dance of particles in the quantum realm. These theories are like constellations connecting the dots of existence, revealing the elegant patterns and underlying laws that govern our universe. Next time you gaze at the night sky, remember, you're made of star stuff and the universe winks back. You are a part of this grand cosmic tapestry, a product of billions of years of cosmic evolution. Embrace your curiosity, never stop asking questions, and continue to explore the wonders of the universe that surrounds us.